Hello everyone, and thank you for selecting this course, Discrete Mathematics. In today's lecture, I'm going to provide an introduction to discrete mathematics. Discrete mathematics, in fact, it's a part of mathematics devoted to the study of discrete objects. Discrete objects are those who we can count. On the other hand, we have continuous data which we try to measure, and counting is not possible. Let me give you some example, like the number of students in class. We can count 5, 10, 20, something, right? And the possibility is something that we can count. For example, between 10 to 15 students, we have possibility of 6 types. Either they are 10, 11, 12, 13, 14, or 15. That's all. But for continuous data, for example, between 0 and 1, right? 0 and 1, there are infinity number of possibilities. Like one example is height of children, for example, between 100 centimeter to 110 centimeter. How many possibilities are there? Maybe 100, 100.1, 100.13, 101.5, infinity, right? That is called as continuous compared to discrete. For discrete data, we use summation. For example, summation of I is equal to 0 to 10, x is what? Right? 0 plus 1 plus 2 plus 10. However, here, if you want to find out, for example, the area under this curve, summation doesn't work, and we need to go for integral. Integral of x1 to x2 and this fx dx, where it is infinity number of possibilities here that we go to count for continuous. We can use discrete mathematics to deal with too many types of problems. For example, you want to know the number of valid passwords. If, for example, the number is, for example, 8 characters, and we have possibility of small letters, capital letters, digits, and maybe symbols, right? Something like this, hash, $sign, something. Then, how many possibilities are there for creating 8 character minimum, something like that? Or, in machine learning, we have some task which is called as classification. We want to try to classify. Let me give you one example. When you want to use your phone, right, you need to unlock. And some new technique, not totally new, but recent, you can say, is face detection. So the camera of your phone try to recognize your face. It's a kind of classification, and it's kind of binary classification. If you are the legitimate owner of the phone, then it's 1. Otherwise, it's 0. If you are, then it will open. If not, it will not open, right? Not unlock, right? We can use discrete mathematics for the shortest path problem. Later we will study, for sorts, for circuit design, and for many other things. There are several important reasons for studying discrete mathematics. For example, we use discrete mathematics to develop mathematical maturity. What is the meaning of mathematical maturity? The ability to understand and create mathematical arguments. Later we will study propositional logics and statements. Also, discrete mathematics is considered as the gateway to more advanced courses like machine learning, AI, deep learning, and something, right? Because discrete mathematics is considered as an important prerequisite for those courses. If you well understand this course, then later you will have a better understanding of those advanced topics. Also, discrete mathematics is a very good foundation for data structure, algorithms, database theory, automated theory, formal language, compiler theory, computer security, operating system, and many other things. So here is the outline of our first chapter. So today we will be studying propositional logic and application of propositional logic. We use propositional logic to better understand and also create some mathematical arguments. Using those propositional logic, we can give precise meaning to the mathematical statements. The rules of propositional logic specify the meaning of our mathematical statements. So, propositional logics are the building block of logic. So, to better understand the mathematical logic, we need to know propositional logic. And the rules are used to differentiate between valid and invalid, where we consider valid as true statements and invalid as false, right? True or false, 1 or 0. These propositional logics can be used in different applications like circuit design programs, verification of correctness of programs, artificial intelligence, machine learning, deep learning, data science, and many other things. In here, we see the definition of proposition. A proposition can be defined as a declarative sentence, a sentence that declares a fact, and it has only two status, true or false, not both of them, not something else. For example, Suwon is the capital of South Korea. The statement is a proposition, although it's false. Washington is the capital of the USA. The proposition is okay, and also it is true. 1 plus 1 is 2, true, right? So these are called as propositions. But these are not proposition. For example, what time is it? If someone asks you, what time is it? And you say true, then he may think that you are not a normal guy, right? What time is it? The answer is not true or false. Or someone tells you, read this carefully, and you say false. So statements should be in that declarative way. We use some notations for dealing with propositional logic. We use small letters for the variables. Normally they use P, Q, R, S, something like that. And also we use capital letters for value. So variables, small letter, values, and values always has two possibilities, true or false. Later you will see 1 or 0 for bits. And here we have some operators. There are 6 common operators. Later maybe we have more, but these are the main operators for propositional logic. The first one is called negation or not, and this is the symbol, not. Conjunction or and this is the symbol. This conjunction or this one. Conditional statement using this right arrow. Bidirectional statement, this one. And exclusive OR, which is shown by circled plus. So these are the operators for propositional logic. The first one is not. Not is simply not, right? Whatever it is, it will convert it. In here, we have only one input, one proposition as input, and then we apply not. Also, it can be shown like this or like this. Both are the same, right? And this is simply opposite side, okay? So if, for example, our statement is today is Tuesday, so the opposite, if this is P, the P naught is today is not Tuesday, right? Or P naught. And this one is true stable that we have for negation. This is input, and this is output. If input is T, output is F. If input is F, output is T. Very simple. The second one is conjunction or and. In here, we have two propositions as input and one will be output. So these two are input and this one is output. Okay, so we can say P and Q or show like this P and Q. In this case, if both are true, the output will be true. If one of input is false, output will be false, right? So here, if today is Tuesday and Q proposition is rainy, right? So P and Q means today is Tuesday and it is rainy. It means if we consider this one as one constraint, as constraint number 1, and this one as constraint number 2, then when AND applies, both constraints must be satisfied, as you can see here. First input is T, second input is T, the output is T. Otherwise, it's F. Both of them must be satisfied. But OR is a little bit kind because he will give us true if only one of input is true. So we call it as this conjunction. We have two proposition as input, and one proposition as output, right? If only one is true, the output will be true. But if two are F, the output will be F. This is always also called as inclusive OR. So here, if only one constraint is satisfied, the output will be true. One is sufficient. The next operator is exclusive OR. In here, we have again two proposition as input and one as output. And the sign is circled plus or O plus. Then, if exactly one of P or Q is true, one should be. So if here only one true, here one true, but if two are true, it will be F. If two are F, it will be F, right? So this is how exclusive OR works. The next operator is implication, right? So in here, also this called as conditional statement. So the implication of P implies Q is the proposition that it's false when P is true and Q is false, and otherwise it will be true. So if P is true, but Q is not following, it means Q depends on P, but P is independent of Q. So if you know probability and statistics, in hypothesis test, we do the same. So P is called as hypothesis, right? And Q is called as conclusion. In here, if P satisfies, Q should satisfy as well. But sometimes make Q satisfied, but P not satisfied because P is independent. Q is dependent. That's why you can see here, if both true, true. If this one true, but F is not true, because F is not following the T, that's why it's F. It is F and T, right? Because for some other reason they come, then it gives T, and for both false, it's true, right? Because they didn't come. I give you some examples. Consider the proposition of P as statement of you go, and proposition of Q, I go, right? So Q depends, right? If you go, then I go. This is the meaning of P implies Q. This is equivalent to P only if. You go, if only I go. That is, you can see here. Let's see another example. Suppose a professor said to you that if you get 100% score on your final, then your score will be A plus. In this case, if you get 100%, you expect A plus, right? But if so, 100% implies A plus. But if you don't get A plus, still you have the chance to get A plus, right? But based on some other factors, right? So this means if 100% lead you to A plus, but getting A plus does not depend on exclusively 100. So there may be a question for you that how can both P and Q be false for this case, but still we have true? For example, I will give you this example. You can read the others. If Bill Gates is poor as proposition P, and pigs can fly at proposition Q, right? So P implies Q is always true. Why? Because Bill Gates is not poor. It means negation of P, negation of Q, right? Bill Gates is not poor, and you can say pigs can fly whenever Bill Gates is poor. Negation of both is correct. So we may consider some conditional statement as implication of PQ. For example, if P then Q, it means P implies Q, if P and Q, P and only Q, and the other things that you can see here. Let's see another example to better understand the concept of implication. If Maria learns discrete mathematics, then she will find a good job. Here two statements are there. Learning discrete mathematics we consider as P, and finding a job consider as Q. So when we say Q when P, it means Maria will find a good job when she learns discrete mathematics. When we say a sufficient condition for Q is P, for Maria to get a job, it's sufficient to her to learn discrete mathematics. And when we say Q unless not P, Maria will find a good job unless she does not learn discrete math, because negation is here. That's why not come here. You should know that P only Q is implication, but we cannot rewrite it Q only P as this one. So it means P implies Q does not equal to Q implies P. Based on the implication, we can create some new conditional statement. Converse is the opposite side. Opposite side of P implies Q is Q implies P. Contrapositive means implication of both and negation. Negation Q implies negation Q. And inverse is negation P implies negation Q. So inverse, contrapositive, and converse. This is an example. Consider this example. The home team wins whenever it's raining. Two statements. Because P whenever Q is one of the ways to express the conditional statement of P then Q, the original statement can be rewritten as if it's raining, then the home team wins. We can rewrite it. Consequently, the contrapositive for this conditional statement is the home team does not win, negation of Q, then it's not raining, negation of Q. So later in HMM, hidden Markov model, we use that kind of rules. These rules seems to be easy, but they are used in many applications. The converse is if the home team wins, opposite, then it's raining, right? Inverse, if it's not raining, negation, the home team does not win, negation of Q. So far, we talk about implication or one direction, right? But we can think of bidirection also. In unidirection, in here we said P is independent and Q depends on P. But in bidirection, both depends on each other. And here we come to the statement of if and only if. It means both constraints should be satisfied. So whenever P and Q has the same value, it's true. As you can see here, same values. But if they are different, it is false. Also called as by implication. Consider this example. P as you can take a flight and Q you buy a ticket. So P by conditional Q or by implication Q, it means you can take the flight if and only if you buy a ticket. The other side is you cannot take a flight if you don't have a ticket. It means both are false. This is for this one and negation will be for here. We can make some complex and compound positions using many others. So you can see here P or not Q implies P and Q. So if we want to go for truth table of this statement, simply we have the possibilities for P and Q here. So these two are input. Then, according to a statement, we will do one by one. So first, we will go for this negation. Why? Because this has the higher priority. Later, I will show you in a table that negation has the higher precedence or priority for the operation in propositional logic. So not Q means whatever Q is here, the opposite side. True F, F, T, T, F, F, T. Then we will go for this one because we have not Q and we have P. So P or not Q, T and F, T, T and T, T, F and F, F, F and T, T. Then we go for implication and we will find out the output. Here is the table for precedence of logical operators. Negation has the highest one, then AND, then OR, then implication, and by implication. Computers work with bits. They cannot understand true and false. That's why in order to work with computers, we need to convert to bits. A bit is a symbol having two possible values, 0 and 1. So we change true to 1 and false to 0. So we can do logic and bit operators as we did so far. Just T as 1, false 0. So in there we had F, F, T, T, we have 0, 0, and some. So these two are input. X or Y, 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 1. X and Y, 0 and Y, 0, 0 and 1, 0, 1 and 0, 0, 1 and 1, 1. X or, if one is different, 1, otherwise it is 0. Very simple, like what we did here. We can do the bitwise as well, right? In bitwise, just we compare one by one. This is OR, this is AND, this is XOR. 0, 1, 1, 1, 0, 1, and we do the same. In here, AND. In AND, it can be 1 if both are 1 only. Otherwise, it is 0. In XOR, if different 1, if same 0. So, this is 0 because they are same. 0, 0, otherwise 1, right? So we call conjunction as bitwise AND, this conjunction as bitwise OR, and exclusive OR as bitwise XOR. We have something called XNOR as well. So XNOR means negation of XOR. So here, once we find out XOR for these two, then the opposite side. So 0 will be 1, 1 will be 0, 1 will be 0, and 0 will be 1. Alright, so far we understand the basics of propositional logic. Now we want to see how they are used. Propositional logics can be used in a wide variety of applications, for example, for machine translation, for system specifications, for Boolean search, logic puzzle, logic circuits, and many others. In the next couple of slides, I will give you one example for each one. Human language, not only English, most, or you can say all of the human language are ambiguous. Why? Because language are created or formed over a long time, right? There is no standard, there is no protocol, logical protocol based on what the language has been made. And because there is no protocol, that's why dealing with them and understanding those things for computers and machines is not easy. So translating sentences into compound statements and other logical expression help us to remove the ambiguity of different languages. And in this way, we try to learn. For example, we want to translate this English sentence into another language, for example, Korean. So first of all, we need to analyze this sentence and make it using propositional logic. The sentence is, you can access the internet from campus only if you are a computer science major or you are not a freshman. In here, we have three propositions. One, we consider this as P, computer science is Q, and freshman is R. As you can see here, P depends on Q and R. Someone is computer science, independent. Someone is freshman or not, independent. But access to the internet from campus depends on Q and R, right? So, if we say this P, P implies Q or. Or means if this is called as constraint number 1, and this is constraint number 2. So if one of them, not both, because this is or, right? If you are a computer science or you are not a freshman, you can access. It means all computer students, regardless of being freshmen or not, can access. And here, all the other department students, they can access, but they should not be freshmen. That's why here we have negation and we write like this. P implies Q or negation of R. So if this is AND, right, then what happened? Only computer science students who are not freshmen, so junior, sophomore, and senior can access. So if we change this operator to AND, all the computer science students except freshmen can access to the internet. So this is how we can use it. This is another one for system specification. We say that the automated reply cannot be sent when the file system is full. When the file system is full. So B consider cannot reply as negation of P. System is full as Q, right? Q implies negation of P, means system is full, then we cannot send the reply. This is logical expression for this statement. Logical connectives are used extensively in search of large collection of information. For example, like Naver, Google, Yahoo, and many other search engines, they use logical connectives to do this kind of search. Because these search employ techniques for propositional logics, they are called as Boolean search. So in Boolean search, we may use connective like AND to match records that contain both of the search terms. Means when we say, for example, New and Mexico and universities, this is a search. This and is a kind of must. It means new must be there, Mexico must be there, universities must be there, right? Universities must be there. We say new, Mexico, university. So it means the search results must include all these three keywords. If this is or, it means universities can be there or cannot be there. It's optional. But when and it is there, and is mandatory, compulsory. And where we say not, it means it must not be there, exclude. And not only this, many other operators can be used for search. For example, if you are going for social media, you use at, for example, at Twitter. If you want to find the price, when we say, for example, you use $, then when you say camera $400, the search results will be camera with $400 price. If you use hashtag, so it will refine those posts or those results who use the hashtag, for example, this one. If you want to exclude something from your results, you can use not, or for example, this one. This is a good example. If you search Jaguar speed, maybe it will give you car speed, Jaguar car speed, but you are looking for animal speed, then you say minus car, only animal should be there. Or if you want to have exact match, then you can go for quotation. It means those two should be there. For example, if you want to search my name in Google, for example, you write Jalil Piran, simply write Jalil Piran, it will give you too many results, for example, Jalil something, Piran something. But if you give into quotation, it will give you only results which include Jalil Piran only. Or if you are looking for a specific website, you can go for this one and so on. Another application of propositional logic is logical puzzles. So for example, we can use this puzzle for logical reasoning, and these help us as an exercise to practice working with rules of logic. For example, this AA is equal to B, BB is equal to D, AD is equal to E. Then what is the output here as a letter, right? So simply you find the position of each one in alphabet, then you go for that. And in this example, it says if this is, then which letter can be here, right? So then you go and you think about it, then you find the position based on this one. So the position of L is 12, the position of N is 16, the position of U is 21, then the position, you will find which letter is here, something like Q. For this one, it is, for this one, because it will be, 1 and 1 is 2, so 1 and 1, 2, then 2 and 2, 4, then 1 and 4, 5, right? Then 2, 4, 5, it will be 11, and 11 is K. In here, so N is 14, this one is 112L, right? 21U, and 17. That's why the answer is Q. Knight and knaves is a type of logical puzzle where some characters can only answer questions truthfully and the other false. What it means? Consider there is one island and two kinds of people are there. Some of them are extra knights. Extra knights always say the truth. They are good people. And some are knave. naive are bad people. Because these people are saying the truth, these people are always liar. Consider you go to that Iceland and two people you will see. The first one is A and the second one is B. A tells to you B is knight. Then the first guy whose name is A will tell you that B is a knight. B is a good guy. And B say to you, the two of us are opposite type. We cannot be both knight and we cannot be both knave. Now the question is, what is the real type of A? A is knight or knave, B is knight or knave. You should prove it based on these two. We first analyze. So we consider P as knight and Q as B as knight. So these two statements. So not P, A is knave because we consider knight here, and not Q is. We first consider, so the answer is here, the statement that P is true. If A is knight, then he is telling the truth when he says that B is knight, because we consider that one. So Q is true, and A and B are the same. But if B is telling the truth when he says that B is knight, so that Q is true, and A and B are the same. But this is not the fact. If we consider B is knight, then they should not be the same, right? So if we change our assumption, we say A is knave and lead us B is knave also. And it makes the original statement that he is liar. He said we are opposite, but he is liar. It means they are the same. So they both are knaves. The next one, the next application is logic circuits. We can use for computer hardware. Logical circuits we can use. So we may receive some input signals like bits of 0 and 1. Then we use some output signals. And here is the shape of logical gates. These are called gates. So this is OR gate. OR gate has 2 input and 1 output. B gate has 2 input, 1 output. NOT gate has 1 input, 1 output. XOR gate, same. NOR and NAND. This is our. If we want to make this one, right? We want to make this one. First of all, we should have NOT. So this is Q NOT. This is one gate. Second, we form this one. So the NOT will come with P and will give you this one. Then we need to one negation here. Then OR of this one, it gives you this. And this is a very complicated for something like calculator. Okay, thank you very much for your attention. I hope you understand the basics. Very easy, but we will go further and we will see some other concept in the next lecture. Please feel free to ask me if you have any questions. Thank you.